Gauss's law is the first of the Maxwell equations, which is a set of 4 equations that completely specify where electric and magnetic fields come from. In particular, Gauss's law tells us how charges make electric fields. From a theoretical point of view, the content of Gauss's law is basically identical to the content of Coulomb's law. In fact, it's possible to prove Gauss's law from Coulomb's law, or vice versa, subject to some pretty chill assumptions. But superficially, Coulomb's law and Gauss's law look pretty different, and they get used in different ways in actual practice. Gauss's law is a statement about the flux through a closed surface, and it reads like so. We take the integral of E dotted with dA, which is a flux, over a closed surface, and we find that that is always equal to the amount of charge enclosed by that surface. Thus, knowing the amount of flux through some box is enough to let you figure out how much charge is in the box. And vice versa. Now notice that I keep saying a closed surface. A closed surface is any surface that completely encloses some volume, like the surface of a balloon. Any surface that doesn't completely enclose a volume is called an open surface. Examples include a sheet of paper or a cup. In Gauss's law, the little circle on the integral sign is telling you that the domain is closed. We can't use Gauss's law to make any statements about an open surface. One thing we need to keep in mind to make things all work out is that field lines going into a closed surface and field lines going out of a closed surface don't count the same towards total flux. The sign convention we have is for lines leaving a closed surface to count as positive flux, and lines entering a closed surface to count as negative flux. To find the net flux through a shape, we have to total up all the positive and negative flux. Take, for example, a spherical enclosure that has a positive point charge sitting outside of it. Each field line made by the point charge enters the sphere, contributing negative flux, and also leaves the sphere, contributing positive flux. Thus, the total flux is 0, which is consistent with Gauss's law. There's no charge inside the sphere, so there should be no net flux through the sphere either. In contrast, take a look at a point charge at the dead center of a sphere. We have a bunch of field lines pointing radially outward through the sphere, and Gauss's law says the total flux through the sphere will be Q over epsilon naught. Note that Gauss's law can make it really easy to find fluxes as long as you know what charges are present. In some special cases, you can even use Gauss's law to find the E field made by a charge. This happens to be one of those cases. Gauss's law says integral E dot dA over the sphere is Q over epsilon naught. And since the charge is at the dead center of a spherically symmetric enclosure, we can be sure that whatever field lines the charge produces will go straight through the outer surface, and will always be parallel to the dA at any point on the surface. If E and dA are always parallel, we can say that E dot dA is just the magnitudes of E and dA multiplied together. And if the charge is the same distance away from the surface at every point, you can be sure that the E field will be of the same magnitude at every point on the surface. And if E is constant everywhere on the domain of integration, you can pull it outside the integral. And last I checked, integral dA is just A. And here A is the area of a sphere, 4 pi r squared. Putting this all together, we can solve for E and recover Coulomb's law, as long as we remember that the Coulomb constant K is equal to 1 over 4 pi epsilon naught. Kind of a cute trick. And we can expand on that trick to solve for E fields in situations we didn't already know the answer for. One word of caution, though. Remember that field and flux aren't the same thing. Gauss's law says that given some Q, You can always find the electric flux through an enclosing shape. But only sometimes, when the shapes involved have appropriate symmetry, can you use Gauss's law to find the electric field. We'll do a worked example that shows just such a special case.